invalidator, right, which in fact is a syntax analyzer. So the generic name for it is a syntax analyzer. We started from a grammar, which we have described here, right? So this describes valid expressions, right? And we, based on this, we wrote a piece of program, right, that validates expressions, returns true when the expression is correct and false otherwise, right? Let's go very quickly through it again, right? And then we're going to turn this into a program that evaluates expressions. So an expression is a term plus or minus another expression, right? If you look here, right, an expression is a term plus or minus another expression, right? So whatever I have highlighted now, taken aside as a separate string, represents a valid expression, right? Then inside a valid expression, or it is a term all by itself, right? So 2 all by itself is an expression. 4 times 1 plus 2 is also a valid term, right? And standalone taken is a valid expression. Now terms are anything where outside of the brackets there's no plus or minus, right? So they're essentially anything without plus or minus, but thinking of the fact that we also have brackets, we might have brackets inside, and inside those brackets we might still have plus or minus, but outside of the brackets we don't have plus or minus. So this, for instance, is a term. This is also a term, right? And this is also a term. So we have a sum of terms. So we can have a standalone term. Now a term is a factor multiplied or divided by another term. And that's true, right? So if we take this as a term, we have a factor multiplied by another with another term, right? Or it can be a standalone factor. Finally, a factor is a digit. We would want to say a sequence of digits, right? But for the time being, let's just consider a case of a digit or another expression within brackets. This is clear, right? As a way of validating, of defining what an expression is. Okay? And let's look at the code. So we're saying that we're going to write code that manipulates a pointer in a string, right? So we have this line that has the expression, and there's a pointer inside it. And whenever we execute expression, this expression advances the pointer as long as it can read a valid expression and stops on the first character that cannot be part of a valid expression. And then if it has managed to read a valid expression from the keyboard, it returns true, which in C is actually the value 1, right? Otherwise it returns false. So to have a clearer example, let's say that my current pointer is here on 1. Well, guess what? 1 plus 2 is a valid expression, and then as soon as we encounter the closed bracket, that's no longer part of a valid expression. It can be part of a bigger enclosing expression, but since my start was here, I have to stop at 1 plus 2, right? And say this is a valid expression and return true for this. And then whenever I return from that, my pointer, my current character, has to be on the bracket, right? So I'm reading the 1 plus 2 and I'm stopping the P on the first character that cannot be part of the current expression. But if I manage to read a full expression, then I would return true. So this is the intention with this function. We're going to have a similar function for term and a similar function for factor. Okay? And then we're going to follow the rules. So this expression is expecting a term. If we manage to read a term, meaning that if this returns true, right? Well, it returned true. So at the point when we're here, it has already returned true, and my pointer is on the first character that is not part of the term. So what is a term followed by? potentially plus or minus, not always. I can have just a single term, or I can have a term followed by plus or minus. If I happen to, if the term happens to be followed by plus or minus, then we can accept this character. So we're going to advance the pointer, right? Otherwise, we're going to, let's say that my P is not plus or minus. Well, guess what? I still have the possibility of the expression being a single term. So since I had returned true here, right, I will avoid consuming the current character and I will return 1. Right? I'm trying to distinguish between the first rule, this rule, and the second rule. So if I encounter a plus, then it's the second rule. If I don't encounter a plus, then it's the first rule. If I don't encounter a plus, then it's the second rule, right? So if the second rule, then I still have to return 1 because the rule has succeeded. But if the star P gives me a plus or a minus, I have to accept this character, so I'm going to advance the pointer. And then from that point on, I'm expecting an expression, right? If I succeed in consuming an expression, I should return true. Otherwise, I should return false. In other words, I should return exactly what the expression is returning. Clear? So I'm just going to, for brevity, I'm just going to return that. There's very, very frequently I see this kind of thing. If expression, then return true, else return false, right? Which is 1, 0, right? This is very bad programming practice. This shows that you're a beginner with capital B. Okay? So whenever you see this kind of thing, the correct way of doing it is return expression. That's precisely the same thing, right? In any language. Okay? Now, what if I haven't managed to read a term? Well, the success of the expression is dependent on the success of reading the first term. If I haven't managed to read the first term, then I should return 0. Clear? All right. Term is exactly the same, just that here we have factor, here we have star, and here we have term. Because expression and term, the rules are very similar, right? They have the same structure. So expression and term have the same structure. Let's look at factor, right? Factor either is a digit, in which case we have the first rule, or starts with a bracket, right? So if we have a digit, then we have the first rule, so we accept that digit, and that's the entire factor. So we return 1, right? Otherwise, if my first expression is open bracket, we're in the second rule. We're doing the second rule here, right? So we're accepting the open bracket. Now we're expecting an expression. So if we succeed in consuming an expression, then we also need to end with a closed bracket. This closed bracket is necessary, right? We're going to test if the current character is a closed bracket. If it is, we consume it. And at the end of the closed bracket, we can return 1. We have read successfully a factor, right? Which is open bracket, expression, closed bracket, right? So at that point, I can return a 0. If I have managed to read the expression, but I don't get the closed bracket, then no valid expression. If I have if I have seen the open bracket but not managed to consume an expression, then again, no valid factor. Okay? Finally, if my factor doesn't start with a 0 or it doesn't start with an open bracket, then again, this is not a valid factor. Clear? Okay. So how do we use this? Well, there's one more thing. At the end of the overall expression, the one that we have here, we have to have the end of the line. I can't have other characters lurking at the end. I can't have other characters lurking at the end, right? So I have to check that the last character on the line is \n. So we're going to read one line. We're going to check that we can consume an expression from it. And then what is left after consuming the expression is the end of the line. Clear? And if this is true, then we're going to say expression is syntactically correct. Otherwise, expression is syntactically incorrect. So if we run this, all right, so if we run this, let's actually use the expression that we had here. Right? We get that this is syntactically correct. Oh, why? Because it has spaces, and we don't allow spaces yet, right? So we're still quite a bit rudimentary. Right? So syntactically correct, and now we can do all sorts of things to it. Let's say I add a close bracket here, incorrect. Let's say I start with an open bracket, but I don't close it, incorrect, right? Let's say I start with a plus, right? It's going to be incorrect, and so on, right? So you try anything you like. At any point, if you have two pluses or you're having two digits consecutively, or the brackets are unmatched, it's going to be incorrect, right? Yes. No, we don't have negative numbers. We haven't. If you want non-negative numbers, you can do something like this. All right. So we can talk about that. I don't want to complicate things too much at this level. So my next step is I want to evaluate this expression. All right. So let's see how we're going to do that. The first thing is we're going to build a tree. So I'm going to copy this expression valid into eval.c, and we're going to open eval.c. Right? Now, if you remember from two lessons ago, we defined structures. Structures are means of aggregating data. We do not have any predefined means of aggregating data, such as list tuples, right, the way Python does. Every time we want to aggregate data, we have to come up with our own structure. And we're going to create one that represents a tree. So we have a node that has a value and two children. So struct node, and we're going to have char c for the time being, and then struct node star left and right. Okay? And the recursion will buffer you, but again, right, think of the fact that you have a storage facility with lockers, right? And then the key is the pointer to the locker, right? So I can take the key to one locker and put it inside another locker. This is what we're doing here, right? This object, right, is much smaller than the structure. It's a pointer to the structure. It's a pointer that goes inside the memory. It has the same size as an integer. It typically has 64 bits. This guy will actually typically have, you might think that it would have something like 17 bits, but it will actually have more like 24, right? Because there's something called alignment in today's compilers. If data is aligned, is placed at certain addresses, then it's faster to access. And compilers tend to be a bit wasteful with memory in order to increase speed, right? So this character C, actually, it will be very lavishly laid out in 8 bytes rather than just 1 byte. It takes 1 byte, and then we would have 7 bytes of padding, and then we would have the 2 pointers, left and right. So it will typically be this kind of, will be 24 bytes, whereas what we have inside is 8 bytes, right? 64 bits. But when you look at laying out this in memory, this guy can point to this guy. This guy can tell me the location of another node, right? Can tell me where the next node is. So we're going to have a node to the left and a node to the right. All right, so this leads to a structure called a tree, right? And I always said that this should be actually called an ear because it has the roots. It's upside down, right? The roots are always up. When we look at a tree, what we call a tree, you got a joke, Franklin? Right? So given an expression 2 plus 3 times 4, right? This is going to be the tree, or 3 and 4, right? So it looks like an upside down tree. Okay. So, all right. So we're going to change the rule. Instead of it returning an int, which was meant to be a Boolean, actually, we're going to return a tree. And actually, we can't return the full tree. We can only return the pointer to a tree. Okay? So if we were in Python, you could conceive of such a thing like returning the tree. And Python actually subreptitiously, right, unknowingly to you, will return a pointer to a tree. But Python tries to hide that aspect from the programmer. Tries to be conceptually clean. All right. Whereas C will actually look at what's there technologically inside the hardware and represent that faithfully. So we can't return the object. We cannot return pointers to those objects. So we're going to return struct node star term struct node star factor and struct node star expression. And then these things, we have to change them here as well. All right. So whenever we succeed, we return a non-null pointer. That is the new truth for us. Right? So that's a tree. Not null means it's a valid tree. If we don't succeed in reading an expression or term or factor, we're going to return null. Okay? Is that clear? So let's start doing that change. So wherever we have return 0, we're going to return null. And then wherever we have 1, we have to return a valid tree. All right. So let's call this left. All right, and now there's a very interesting aspect of C. All right, so when we have term, so this should be not equals null. All right, so that's what true means now, not equal to null. But there's the following kind of construct that I haven't introduced previously. I can say node is assigned, sorry, left is assigned term. Now, this is an assignment, and we have seen assignments before, right? But it turns out that the assignment is also an expression. And the result of this expression is the result of the left-hand side of the assignment, right? Because of that, I can say things like A equals B equals 1, right? So the equal operator associates to the right. And then we're going to have this assignment is performed, but it's also an expression. The result of this expression is going to be 1. And then A can be assigned to the result of the expression and will continue to be assigned to 1. All right? So in this format, it's not very useful. It's very seldom that we want to put the same value in two variables, but sometimes we want. But it is very useful inside conditions, right? I can assign and test at the same time. So I can assign the result of term to variable left. Let's get rid of this one. I can assign to left, and then the result of term also check whether it's null or not. So there's two things happening at the same time. Okay? Many people criticize this, right? Anyway, it is standard idiomatic C. It is used a lot. So we have collected the potentially left child of my expression in this term, right? Yes? Now, we cannot simply return expression anymore, because if this succeeds, so let's create a right here as well, and it's also a pointer. So if expression succeeds, so I'm going to have right. So I'm going to preemptively assign right to expression. And notice the extra level of brackets, they're necessary. Not equal null. So, and we're going to have an else at some point. So if this has succeeded, now left is the left subtree and right is the right subtree, right? So imagine we have something like this. 2 times 3 plus 4 times 5, right? So if this is the first term and this is the second expression, right, in our code. So if this has succeeded, the first call to term, which is the left, right, the left is going to look like this. And if the expression call succeeds, I'm going to have something like this, right? So this is going to be my left, this is going to be my right, right? And now I have to take this plus and create this. So at this level where we operate now, we are assuming that this is done, and this part we have to build. Okay? So what do we do? Well, we're going to need to have a result. All right? So let's add the result here as well. And what do we do with a pointer? Before using it, we have to, louder, initialize it, right? Allocate space. So here, when we get the result, we're assuming that the allocation has been done inside here. The same with expression. We're assuming that the allocation has been done there. But we're creating a new node. And as we create the new node, right, we have to fill up the C, the left, and the right. Before being able to fill up the C, the left, and the right, we have to allocate space. We allocate with right? So always you have to assign something to result before filling up stuff. And now we can say result dot arrow left. So this is the left component equals left. Arrow right is right. And result arrow C equals what should I put in there? Right, so I should put the star P that I had here, right? Trouble is, by the time when I reach here, I have already advanced that P, right? So one thing we should be doing is take a snapshot of what it was at that point. So let's add a character here, and then we would, right here, before doing the P++, we would say C is assigned star P, right? And then result arrow C is C. So now all these guys, all these fields that we have here have been filled, right? All fine? So then what's left is to return result. Okay? Else, on the else branch, well, it must be the case that this guy returned null, right? So all I can do is return that further. Right? Because the expression has been unsuccessful, and the way to signal the fact that it has been unsuccessful is by returning null. Okay? Now, what do we return here? So this is well, I have to access the component inside the node, right? When we were in Python, we would do object dot field, right? So the same we can do in C, we can do object dot field, but we don't have the object. We have a pointer to the object, right? So if we have the pointer to the object, we could say star result dot left. But this is cumbersome, right? So the arrow is a shortcut. All right? So result is a pointer to a structure. And I actually should oops. I don't know. I should be able to. So this is a pointer, right? To an object. So then this is the object. So then the object dot left is the field called left inside the object. Okay? Yep. So then what do we return here? So previously we would return 1. It was successful. But it was successful by reading term and not finding a plus or a minus, right? So it's the success of term alone. So what should be the result? Louder. Well, term is a function. Louder. Left. Yes, very good. Right? So the tree created by term is here. And I don't have a right because this part has not been successful. Right? So meaning that the first rule has not been successful, we resort to the second one. The second one is just this. So meaning that left is a valid result to return if this term is not followed by plus or minus. Okay, so we're going to return that. Okay? So we need the same kind of transformation here as well. So I tell you what, we're going to take this because it's easier and replace here. And now we have to be very careful in making all the changes. So this is factor, right? This is star. This is division, right? This is term. Okay. Is there anything else? So factor term. That should be it, right? And let's look at factor now. Right? So whenever we have plus or minus or star or division, right, we create a node where the left and right children are definitely not null. How about a case when what we encounter is a digit? For a digit, right? For a digit, there's nothing below a digit, right? But the node, this is a node, right? Must have a left and a right. We have to put something there, right? What do we put? Null, right? So null. So because I'm just an engineer, we were in, we go to the null like this, right? So you're actually grounding the pointer. So the left and right should be null, right? That represents the fact that this is a terminal node. There are no descendants from there. So let's start building the node. So this time I am going to build the node up front, right? So I'm going to say struct node star n or result, which is equal to struct node star m alloc, and we're going to have size of struct node. Okay. Have I forgotten any semicolons, which I tend to do these days a lot? I'm not coding in C every day. All right, so we're creating the result, right? So what do we fill in with? So we're going to have result C equals star P, right? Because we are not reading past this. And then we also have to do result And because this is surely a terminal node, right? We can actually prepare everything here. We can say node left, and actually we can make it a bit faster by saying right equals null. So this is one case where the chained assignment becomes a bit handy. Okay? So we're going to return a result. Right? Now for the next rule. So we're going to call expression here, right? And we're going to say if result is assigned expression and not equal to null, right? What's the effect of brackets? They do set the precedence, but in terms of tree, it doesn't do anything to the tree, right? The tree I get from expression is the tree I pass from the factor, if I get an expression. Brackets don't add anything. Okay? So in that case, right, if I get here, I can simply return result. Okay? And otherwise we return null. So now notice that in this part of the program, I don't need the result. I don't need the allocation at all, right? There's an allocation that happens here, which means that this allocation might be redundant. And when it is redundant, it actually wastes memory. So what we're going to prefer to do is take this allocation and this text editor is very buffering. I'm going to take it here. Okay, so we only need to allocate in this case. We don't need to allocate for both if statements. So we put the allocation inside. Okay, and we're pretty much done. Yes? Which C? Well, it is defined. It is defined here. Okay? What do you mean define it again? So this is separate from that C. Okay, so let me call this D. Does it make sense now? The fact that I chose the same name is coincidental, right? It is a character, so I want to represent it as a character, right? But this name and this name has no relationship to each other, all right? So this is a variable that I use to record the value of the current character at this point, and then I put it inside the structure at this point, right? And there's no name clash. The fact that the name is the same, the name inside the structure is in a completely separate namespace from the names outside of the structure, right? So I can use the same name for both, and the compiler doesn't get confused, right? Since the character, I prefer to call it C because it's more obvious. It's a character, and then, but it's not. It's defining a completely separate variable. Okay? Yeah. at the bottom. Yeah. Yeah, result. Good catch. Very good catch. Okay, very good. Okay, so what shall we do? Well, we need to evaluate. Before we evaluate, actually, let's evaluate. Let's do an evaluation. So one thing I would like to do is do a compilation. So let's see if this should still work. So let's gcc minus o eval eval.c and 9 line 9, forgot a semicolon. Yes, so remember the weird rule. After structures, in spite the fact that it's after a closed brace, we need a semicolon. Nowhere else after a closed brace do we need a semicolon, but. And then we also need stdlib.h. that contains the prototype for malloc. All right, so it compiles, and let's see if it still works. It works, great. So how do we evaluate? So let's write a function int eval, and we're going to take a struct node star n, and return the result. Okay. So any thoughts? What would be the cases? Let's look at my current node. It can be looking there. It can be. Can we find two different categories? Yes, versus. So this is a node, this is a node, this is a node. So we can have operations versus operands, right? Versus numbers. Which one is easier to tackle? The numbers, right? If I see a number, that's the value of my expression. Right? So if n c all right, so 0 as a character, right, is less than equal nc, and nc is less than equal 9, return. How do we get the value? Yes. Right? And this has to be converted to an int. If we don't have a character, it must be an operator. Right? And if it is an operator, that node also has two children. Always two children. It cannot have one child, right? So let us evaluate the left and right children, get their integers, and then perform the operation. And on this occasion, we're going to learn a new statement. So we're going to say int left equals eval of no n left, right? And right okay. So these left and right are now integers that represent the results of the underlying expressions, right? So then we have to combine the left and right into a value, right? And it depends on the operator at hand. So we could write a sequence of ifs, but it's easier to do it with a switch statement, which you haven't learned in Python because it doesn't have one. So we're going to dispatch on the value of C, which can be star, which can be plus, minus, star, or division, right? So case plus, right? So we're going to return left plus right. Case minus, return left minus right. Star, left, star, right. Case division, return left, division, right. Now, there's many characters out there, right? What if the character is none of plus, minus, star, and division? So that won't happen if our program is correct. But generally, in general, we want to be defensive. And I'm also telling you this because I want to teach you the extra element of the switch statement, which is the default. So if no match, right, we can have a branch that applies to all remaining characters. And what we should do here is actually print an error message. And perhaps a good thing would be to exit. So we're going to have exit 1. Okay? So in our case, this will never happen. And it's no error to not provide one, but it's good practice to always provide a default. And if you're never expecting to reach here, if you're expecting your program to never reach there, then what you should do is an error message and an exit, so that if there's a bug and you, by mistake, reach there, you would figure that out. So now, if our expression is correct, so we're going to provide an int result here, and we're going to say right, we're going to say result is %d \n and result. And this should be our program. Okay? Oh, not expression. Sorry. Not expression. So we should say struct or node or tree equals expression. All right. Int result equals no, this is not good. So if 3 equals expression, then we don't need the result here, sorry. And then we're going to say eval 3. Okay, so we're doing as before, right? We're executing expression. If this guy is null, then the expression is syntactically incorrect. So all we can do is print the error message and go, right? Otherwise, we want to evaluate it. So instead of, as before, just printing that it's correct, we perform the evaluation here, and that should return a integer, and we print that in. Okay? So let's do this. Okay, 1 plus 2. Result is 3, right? So 1 plus 2 times 3, right? And notice that the precedence is correctly done, right? So 2 times 3 plus 1, again, right? It's correctly done. It's not, you have to stretch your neck. Okay, so let's do it here. Right, 2 times 1 plus 3, 8, right? So we're looking at, correct usage of brackets, correct precedence of brackets, and so on. So there's something, though, that doesn't work correctly. Okay? So I'm going to do 9 minus 3 minus 2. Okay? So it's going to be homework why this happens, and next time we're going to fix it. All right? So look at it and try to understand why that happens, and we're going to try to fix it next time. Okay? So for the time being, I want to pause a little bit and allow you to mull over and ask questions. This is a relatively sophisticated program, right? But this is pretty much what C is good for. C is good at implementing other languages, right? Python is implemented in C, Java is implemented in C, entire operating systems are implemented in C, including the Mac operating system, the Windows. Windows actually, they claim it's C++. Linux is in pure C, right? So it's good at providing these very basic tools, operating systems and compilers, right? And what we have done is essentially along these lines of we actually have not really a compiler, but rather an interpreter. But we're essentially parsing a little language and performing language processing, right? Which is very typical of C. So think a little bit about it. Do you have any questions? Take 2 or 3 minutes while I'm still here and I can answer them. And then I have a little puzzle that would probably not take too long and be fun to solve. Look at every line and wonder why it's there. And if it's not clear to you why it's there, ask me why we should write it in that way. Yes. Yeah. So it's not equals, it's a sign, right? So I'm executing expression. The result of the expression is a 3, which I'm putting in this variable. But this construct even though it's an assignment, it also counts as an expression. Therefore, the value of expression is the value of the entire bracket. So I can further go. Now, you're saying it's a pointer, but the pointer is ultimately an integer, right? And the null pointer is ultimately 0. Okay? So it would probably be a lot better to say not equals null. All right, that would make it a bit more obvious that this is a pointer. So the reason why whenever we make comparisons with pointers, we write them like this, right? It's because we want to make it obvious that it's a pointer, right? Otherwise, if I'm comparing against null or not null, I can drop this, right? Not equal to null, I can just drop it because it's going to be a pointer, which is ultimately an integer. It's 64 bits, right? So if it's 0, it's false. If it's not 0, it's true. Okay? So that's what's happening. Expression gets executed, the result is put in tree, but we're still inside the if, and we can conditionally perform branching. Okay? Everybody's okay with this? Or is it the case that you're so puzzled you don't even know what question was? Okay, we'll move on to the next thing. Yes. Factor. Well, you have something that doesn't work for you? What's the error? Oh, did you copy this? Do you have this line? Do you have these two lines? Do you have these two lines? No? So probably that's the reason. Okay. Next little puzzle. All right. So let's say, well, we're in Singapore, right? I haven't seen coins in quite some time, to be frank. But what are exactly the coins? What are the denominations? We have 5 cents, 5 cents, 10 cents, 20, 50, and $1, right? So we have four coins that are less than $1, right? If somebody gives you $1 and you have to return change, and you have unlimited amount of coins, right? In how many ways can you return change? And we're looking at a change as a set of coins rather than the ordering. So we could return two 50s. We could return a 50, two 20s, and 10, right? You could return 5 20s. You could return 10 10s. All sorts of combinations of 20 and 10, right? Then we move on into 5. And the question is not to enumerate all. We could enumerate all, but how many such possibilities exist? So if you were to solve this problem, how would you approach it? But it has to deal with recursion. It's not a problem specific to C. Again? Mm-hmm. So can you? So remember what I said a few times ago when it was the problem of solving the powers of Hanoi. What was a very good thing to do in this kind of problems? I'm saying you give me change for $1. What did I do wrong here? Louder? What do you mean specify? Generalize, right? So we did the same thing in Towers of Hanoi. We said, move me the disks from pole 1 to pole 3. Why restrict ourselves from pole 1 to pole 3? So in this case, why restrict ourselves to $1? I have some amount, and then I want to get change for that amount. Okay? So assuming that I know how to give change for a smaller amount, I have an amount C, right? Assuming that I know how to give change for a smaller amount, how, or not how to give change, to find out how many ways there are to give change for a smaller amount. How can I use that? Mm-hmm. Mm-hmm. Can I reduce it to just 2 choices? So there's another thing that we can generalize, right? Why restrict myself to specific denominations? 50, 20, 10, and 5. Let's say I have a list of denominations, right? So how do you do it now? It's a lot easier, actually. Yes? I need a single choice. I want one choice. Yes, but at each step I want one choice. I can either do this or that, right? That's one. That's one. Well, you can call that 2 choices, but me it's the choice and the negation of that choice. So what would be a good choice? I can either do this or not do this. Um, so think of in terms of actions that we can perform. Give change is not an action that you can, right? So what you want to build this solution, right? What is your action? Your action is I can pick a coin of this or a coin of that or a coin of that, and I can have a partial solution out of that, right? And then I can move on to the next step, or I can choose something else, right? So it's a sequence of picks. My action is picking a coin, right? So if I'm up front and I have an amount C and I know how to count the change for any amount C prime smaller than C, what choice can I make? But when I say smaller, that's very vague. Now I have multiple choices, right? I just want one choice. Well, what's C prime? Because I said any C prime, right? So if C is $1, C prime is anything less than $1. So how do I pick that C prime? Again, I have too many choices. But I only have a finite list of denominations in, let's say, decreasing order. Okay, you're getting closer. Okay, so I can either use the largest denomination or not use it at all. Right? That's the choice. So I can either use it, which means that I take that, if I use it, let's say it's 50 cents, right? I have to count the ways of returning change to 50 cents, which I know how to do, right? Or I decide to not use it at all. So I have to return change to $1 using only smaller denominations than 50, right? Is it clear that that will exhaust the space of, will give me all possible combinations? And will be giving all possible combinations because I'm considering the coins in decreasing order. So that's a relatively important aspect, right? Because I never want to, actually I'm not sure that's important. But is that kind of clear? So we're going to start with defining denominations. And I'm going to introduce new things yet again. So I'm going to introduce an array, static array of denominations. And here we're going to say 50, 20, 10, 5. And it works very well with any other denominations. You will see this question with American denominations most typically, where there's a 25 instead of a 20. And there's a 2 cent as well instead of, so there's 5 and 1. There's 5, 2, and 1. All right. So we're going to return an integer, right? And then what are the arguments? Int amount and int the number of denominations that we allow ourselves to use. Okay, so now if amount is equal to 0, all right, let's start with if amount is less than 0, because it can happen. Error? Are you sure? So how many ways have we discovered? 0, right? So if it is equal to 0, how many ways have we discovered? 1. Right? So we're returning change for 0 cents using 4 denominations. I give you nothing back, and I discovered one way of giving you change, right? Think, people, think. All right? Else, return count change of, so either I use right of count. So we're going to start with a count of 3, right? Actually, this is wrong. I want them in exactly the opposite order. So 5, 10, 20, and 50, right? So amount minus denom of count, and we're going to start with a count of 3 here, right? Plus and count, right? So if I use it, I am continuing to use it, right? So I'm going to use count denominations, right? plus count change of amount. So I choose not to use that denomination. So now because we have count minus 1 here, guess what? This guy might become minus 1. What happens if this guy has become minus 1? How many ways of recurring change have we discovered? 0, right? So we can add this here. And this is the solution. Okay? This is a very typical interview question. All right? We don't need the braces here. We want to become a software engineer. And obviously, it will be interesting if all these can be parameterized and read from the keyboard, but we don't have time now. Let's see how many ways we can give change to $1 in Singapore. And 3. Not minus O. Segmentation fault. Segmentation fault is probably because the only place where the segmentation fault can happen is here. Oh, is it because I think we're in infinite loop. Infinite loop. So we're exceeding the recursion depth. That's what's happening. So it's becoming negative. Sorry, it should be or. See how tricky it can be? 99 ways. Okay? So try to print them out and convince yourselves that they're all distinct. Right? Another way would be to see if you're in the States. Right? You would have 1, 2, 25, and then we should start from 5, right? And see how many ways in the States. Much more. Okay? Somehow I remember that number to be around 80. So I'm not quite sure what was missing. Maybe there was no 2. Maybe there was 2 and no 1. I can't quite remember. So of course, if we change the size of the array, this should be 4. So you see, the problem with C is that it never tells you where the error is. You get a segmentation fault, and that's it, right? So obviously, the size that I put here has to be correlated with the size of this array, right? I have to point at the last element. If we don't do that, we get this error. There's absolutely no indication where to look for the error, right? So you need to be a bit experienced, and this is why C is such a dangerous language, because it might happen one day after writing 1 million lines of code that, oh, you have this sudden segmentation fault, and all that work goes down the drain if you don't find it, right? And sometimes it can take months to find it. So, is this clear? Questions? So I probably will ask you to print the distinct combinations as homework. I think it's a good idea. Take this. Okay. Questions? Yeah. Again? So again, you can choose to use a denomination. So if I use it, if I pick it and put it, so I'm building a partial solution, right? So imagine that I'm here. I have a stack where I'm building up $1. I'm trying to build an amount of coins that goes up to $1, right? So I have many piles of 50s, 20s, whatever, right? So I can choose to pick a 50 and put it here, right? Or I can choose to not use 50 at all. So if I take a 50 and put it here, what am I left with doing? I don't have a solution yet. I should continue to return change for $1 minus 50 using all the denominations, right? If I have used the 50 right now, I can still use the 50 in the future, right? So, and I'm going to continue, and I'm going to find a number of solutions for returning change to a 50, right? So I've already picked a 50. I'm left with another 50, and I have I will find a number of ways of returning change to that 50. So that is part of my solution. The other alternative that I have is to not use the 50 at all. So I still have $1. That was my choice, right? And then I'm taking the 50s aside, I'm putting them aside, and I'm going to use the remaining denominations, right? So from that, I have a new problem, and from that, I'm going to find out a different number of ways of returning change to $1, but using only 4 denominations or 3 denominations. Okay, so the sum of the two is going to be my total number. Cool? Okay. Don't underestimate recursion. It's one of the most powerful problem-solving mechanisms. Okay.